centered around three main topics. One topic is multi-target prediction, which is a kind of umbrella term for complex machine learning settings like multi-label classification, multitask learning, direct prediction, matrix completion, and so on. This is kind of the main topic on which I've been working in the last 10 years, but I'm not going to talk about that today. Then a second line of research is sequence models and time series analysis. This includes sequence labeling, autoregressive models, feature learning for sequential data, etc. And a third line of research that we started up maybe a bit more recently is uncertainty quantification, which includes like base optimal inference, epistemic and aleatoric uncertainty, etc. And actually the talk of today is going to be a mix of those two last research lines. And in terms of applications, as Philippe already said, I'm mainly working on bioinformatics data, omics data in particular, for environmental and medical applications. And we're also working on climate analysis. So let's come to the topic for today. So I'm going to talk about time series forecasting, and I'm going to start with three motivating applications that are kind of central for the time we are living for the moment. So the first application, quite obviously, is COVID prediction. This is a picture from a while ago where we were still in like the third wave, I think. But of course, when we're talking about hospitalizations or people at intensive care, it's quite obvious that we would like to be able to predict that quite early in advance. Let's say next week, in 2 weeks, in 1 month, how many people are we going to have in the hospital? So that's an example of the time series forecasting problem. I have a second example, something that's also quite important for the moment. Last summer we had in Western Europe those serious floodings where rivers got the kind of level of water as never seen before. And also in this type of settings, you would like to be able to predict quite early in advance what would be the river level that you're going to get. So typically 24 hours in advance, 48 hours in advance, so that people can evacuate on time. A third application, also quite hot for the moment, is the energy prices that are also peaking. And here again, it's time series data where we would like to predict in advance what it's going to be the price of electricity or gas. Now, in all those three applications, you not only want to predict what's going to be the price next week or 1 month later, but you also want to have some uncertainty about that. You would like to have some kind of prediction interval that you know with certain guarantees. Yeah, the price is going to be between this price and this price, for example, with a 95% confidence. So that's going to be the topic of my talk of today. And actually, the talk is separated into two parts. In the first part, I'm going to talk about the classical regression setting where we have IID data. And then in the second part of the talk, I'm going to extend that to the time series forecasting scenario. And we're going to focus on the distribution-free setting, which means that we don't make too many or if possible, no distributional assumptions of the underlying data. So for the first part, for the regression setting, we have kind of this situation. I have some predictive variable here. In this case, it's speed. And we have a response. And we are not only interested in predicting the mean, but we are also interested in predicting the uncertainty around that. So for the first part of my talk, I'm going to show you some results of a comparative study where we compared several recent methods from the literature, and this paper here summarizes those findings. It's still under review, but you can already find it on arXiv. So let me start with formalizing the problem setting a bit more formally. So Usually in regression settings, we have a point predictor for which I will use the notation rho. That's a mapping from our feature space X to the real numbers in case of regression. So think of rho as predicting the mean or predicting the median. But in this talk, we are not going to predict the mean or the median. We're going to predict an interval, which is a mapping from X to all possible sub-intervals of the real line. And I will use the notation gamma for that in my talk. And in the first part of the talk, we are going to talk about the classical regression setting, which means that we have our training and test data are independent and identically distributed according to an underlying distribution P over X times the real numbers. We're going to be interested in three main performance measures for this interval predictor, the three measures that you most often see in the literature. And the first measure is what's called the marginal validity. What is this? So you're going to specify a certain coverage level that you want to achieve 1 minus alpha, let's say 95% coverage. Then we will say that our predictor is going to be valid if we take a random sample from the underlying distribution that in at least 95% of the cases, the true label, the ground truth, is part of the interval that we predict. So the probability that the true label is part of the interval has to be at least 95%. In practice, we will replace this expectation by just an average on our test set that we're going to compute. So this is usually called marginal validity. Now, if you replace this inequality here by an equality, that it has to be more or less or exactly 1 minus alpha, then we speak in the literature often of calibration. And then another measure that we're going to use here is then a kind of side measure. So this first measure, this marginal validity, is going to be the most important measure. But then a side measure that we're going to use is this one over here, which is going to look at the width of your interval. So we have our upper bound of the interval, we have our lower bound of the interval. You just look at the average width over the test set. Again, this expectation can be replaced by an average over a test set. So these are going to be the performance measures we're going to look at. And I would like to discuss with you 4 groups of methods in the paper that we published. We separated the methods from the literature in 4 groups. And the first group of methods are Bayesian methods. So for the people that are not so familiar with Bayesian methods, you start with a prior probability distribution, a prior belief over the parameters of your model. And then once you see a data set D, you're going to compute the posterior distribution over the parameters in this way with this formula. And when we have this posterior distribution over the parameters, when we get a new test instance, we get new instance X, we can compute the posterior probability of the labels for that particular instance X by computing this integral over here. So this is how this goes in general for Bayesian models. Now there's 2 very popular instantiations of that in the literature, namely Gaussian processes, where you have quite strict assumptions about the underlying model class, and where typically exact inference is possible. And then recently in deep learning, Bayesian neural networks have become popular, which typically have less assumptions compared to Gaussian processes, more complex model classes. And for that reason, only approximate inference is possible, because those integrals that you have over here become impossible to compute analytically. So let me show you some results, what we obtained for Bayesian methods when we are using these for computing prediction intervals. So I'm going to have quite some slides where I show pictures like this. So let me explain this a bit. On the x-axis, we see different data sets. Now for Gaussian processes with exact inference, that's what we show on this slide. there were only 8 of the 10 data sets where this exact inference could be run. So you only see here 8 data sets on this slide. On the coming slides, you will see 10. And then we will have 3 metrics that we look at. In orange, you will see the R squared, which is the kind of typical performance measure for point predictors. And the data sets are ordered always on the slide so that this increases. So here we have like the most challenging problem for which the R squared is the lowest. And here at the end on the right, we will have the problem for which the R squared is the highest. Then in green, we will have the average width of the intervals we compute. So typically, if the problem becomes easier, also the width of your intervals is going to get smaller. So this is in general a decreasing function. But the most important performance measure we're going to look at are those blue curves. So in the next graphs, I would like you to focus on those blue curves, which denote the coverage. And in all those experiments, we're going to aim for a coverage level of 90%. So what do you see with Gaussian processes? So you have some error bars here. It's because we do some repetitions of randomly splitting training and test data. You see that in general, on those data sets, this works quite well. You have sometimes that don't have this coverage of 90%. You're a bit above. Here on this one data set, we were clearly under the 90%. So yeah, for most data sets, this went quite well with Gaussian processes, but you're not always achieving this validity of 90% as you would like to have. Let's see what this gives when we replace exact inference with approximate inference. In this case, this was a variational inference that we used. Then you see that yeah, here we get quite conservative. We're much above this 90%, so this is not good. Here we get quite wide. So yeah, the results got a little bit worse, which is kind of reasonable because you replace exact inference by approximate inference. Okay, so this is the first group of methods. Then the second group of methods are ensemble methods. With ensemble methods, yeah, it's quite a diverse group, and there's many different approaches you could consider here. But let's say the 3 types of methods that are for the moment quite popular to use in practice are random forest, dropout networks, and deep ensemble. So in random forest, the ensembling comes from taking bootstrap replicates of your training data set. In addition, you sample, you make the variables that you use in each decision tree random. In a dropout network, the randomization is going to come by randomly leaving out some nodes in your neural network. You can do that at training time, but you can also do that at test time. And then you get an ensemble in that way. In the case of deep ensembles, we run training with different initializations of the network, and you get an ensemble in that way. So 3 different ways to end up to an ensemble. Now, the most naive way to construct a prediction interval with ensemble methods is the following way, where we compute the variance over our predictions of the different ensemble members, and then you assume that this distribution of the predictions for the different ensemble members, that they follow a Gaussian distribution, and you're just gonna construct a Gaussian prediction interval by looking at the z-scores of the standard normal distribution, so the z-scores that are connected to this confidence level alpha that you want to achieve. That's the kind of most simple and I would say perhaps most common approach to use ensemble methods to create prediction intervals, but it's not always a good approach, as I will show you in the next slide. So this is the example with, if you do that for dropout networks, and for dropout networks, we really got results that sometimes don't make sense. So as I said already, we have to focus here on the kind of blue curve, and we see that, in almost all cases here, we don't get at this 90% coverage that we want to achieve. So this didn't work very well. For example, if we do this with deep ensembles, the results were much better, but still here you're under the 90%, here you're much above the 90%. We still were not really calibrated with those ensemble methods. Okay, third group of methods. The third group of methods in the article, we have called them direct interval estimators. And the most famous example of such a method is quantile regression. So instead of modeling a regression function that's going to estimate the mean, for example, we're going to immediately model the lower bound and the upper bound of our prediction interval. And in case of quantile regression, this means that you replace the typical least squares loss by another loss function, the pinball loss, which has this, you have this parameter alpha in it, which is the coverage that you want to achieve, which is actually the quantile that you're modeling. So you'll have to optimize this loss for the two different quantiles you're interested in, the one that represents the lower bound of your interval and the one that represents the upper bound of your interval. Now, recently, there have been a couple of ICML and NeurIPS papers where they use other loss functions for example, weigh the two criteria that I mentioned a few slides before. This MPIY, this is the mean prediction interval width. So basically this criterion that I had 4 or 5 slides before. And then the second term is related to the coverage. So C is here the coverage. So this is here now a loss function that's not decomposable over the instances. You compute the coverage over your whole training data set. If your coverage is smaller than 1 minus alpha, then you get the penalty here in this term. Otherwise, this is going to be 0, and you have this lambda that's going to weigh off those two criteria with regard to each other. So that's another type of loss function. I would argue a bit less principled than quantile regression, but it's also something that you see in the literature. So let me show you the results that we obtained with quantile regression. We were not always at this 90%. Sometimes we were really under it. So for example, for those 3 data sets, you're closer to the 80% than to the 90%. For other data sets, this worked quite well. So we also see here with this method that we don't always get the coverage that we would like to aim for. Okay, last group of methods is conformal prediction methods. It's a group of methods that have become quite popular recently because they have some nice properties. I'm going to explain you here one particular conformal prediction method, which is called inductive conformal prediction in the literature. And the idea behind this inductive conformal prediction is that you're going to consider a validation data set, and then we're going to calibrate our intervals on this validation data set. So how does that go? More specifically, we're going to compute non-conformity scores on this validation data set. There's many different non-conformity scores in the literature, but when you have a point predictor, then the kind of most common non-conformity score is just the absolute residual. So this rho of X, rho was our point predictor, let's say the mean, and then YI is the true label. We just take the absolute difference between those two, and we're going to compute this absolute difference for any observation in our validation data set. And then we're going to sort all those values, and we're going to compute the 1 minus alpha quantile of it. Actually, it's not a 1 minus alpha quantile, but a small finite sample size correction. So you see here the size of the validation data set appearing into it. So you multiply this with something that's a little bit bigger than 1. This quantile is what we're going to consider. And what is then our predicted prediction interval for a new test instance? That's going to be all the labels for which the nonconformity score is smaller than this quantile you have just computed in the step before. So that's how we're gonna generate our prediction interval. And then you have this famous theorem that says that if the nonconformity scores are exchangeable, which is a slightly weaker assumption than IID, then this interval will become valid when our validation data set grows to infinity. So this is a nice theoretical result to have for inductive conformal prediction. For other variants of conformal prediction, you can derive other validity results which are slightly different. So let's see what this gives in practice. So let's go back to this quantile regression that we had a few slides before, where we had like here, here, and here. We didn't have the coverage that we wanted to achieve. I hope that everybody can see my mouse, but it's the first, the third, and the fifth point I'm pointing to on the blue curve. So if you're now going to apply conformal prediction in addition to this quantile regression, so maybe I have to say we can apply this conformal prediction to any of the methods I've discussed before. It's a general approach where you can recalibrate your intervals in a way. In the case of quantile regression, we won't have a point prediction, so our non-conformity score is not going to be this score that I was showing here on this slide, but it's going to be a different one. But if you apply that, then you get something like this. And we see that on average, we always obtain this 90% coverage that we wanted to have. So this is an asymptotic validity. This means that on a finite test set, yeah, you can be under the 90% or above the 90%. So you still have some variance here. There are other conformal prediction methods that have smaller variance, but you see that, okay, on average, we are nicely at this 90%. Sometimes we're a bit above, sometimes we're a bit below, but on average, you're at this 90%. So to summarize the first part of my talk, where we focused on the traditional regression case, here is a bit of a slide with a summary. So if we compare the four groups of methods with each other, what do we see in general? That if you look at the criterion marginal validity, that actually only conformal prediction can give you some guarantee of validity in the distribution-free setting. Bayesian methods can also do that when the underlying assumptions are correct. In terms of scalability, we see that, yeah, for Bayesian methods, there's sometimes an issue that you have to apply approximate inference instead of exact inference. In terms of incorporating domain knowledge, if you have some background knowledge about the underlying distribution, typically when things are Gaussian, then Bayesian methods might be the right way to go. And then in terms of the usage of a validation data set, typically the direct interval estimation methods and conformal prediction methods, they need a separate validation data set. In the case of quantile regression, for example, this is to fine-tune some hyperparameters of your model. In case of conformal prediction, it's to recalibrate those prediction intervals that you have. Okay, that brings me to the end of the first part of the presentation. I was planning to have a small break here for questions, but because there's a problem with the sound, I can't hear anybody. So maybe I would propose to leave the questions for the end of the talk, if that's fine for everybody. For the moment, I also don't see the chat, but maybe when I'm at the end of my presentation, I will open the chat and we can have some questions in that way. So, okay, let's now come to the core topic of the presentation, namely the extension of these results now for time series forecasting. And what's going to change in the time series forecasting setting compared to the classical regression setting is that now our observations are going to arrive in sequential order. And I will focus on the one step ahead forecasting scenario. Let's say we have a frequency of daily observations that we get, and we want to predict one day in advance. The results I'm going to show can be easily adjusted for other horizons. I see that I get a message here. Let me see whether this is from the organizers. Okay, I don't get the message that I received from the organizers, but I guess for the presentation we're still fine. Yeah, so in the one step ahead forecasting setting, we basically want to build a prediction model where we have, I still use the same notation, this row for the point predictor. That's going to take our history as input to make a prediction for time step t plus 1. So typically we can have also covariates observed at time step t plus 1. Think about the river flooding example where we want to predict the level of the river at time step t plus 1. We might have some estimate of the wind speed or precipitation at that timestamp. And then also like the data from previous timestamps you're going to take into account. And then, yeah, we will make a prediction with that and we will make some error. And it's all going to be about those errors because those errors need to have some properties for some of the methods we're going to use. So what are the main challenges in this setting? To my opinion, there's three main challenges. I would like to talk about all three a bit further in this presentation. The first challenge is autocorrelation, and I will argue that it's quite easy to handle that. The second challenge is going to be heteroskedasticity. And this is going to be more difficult to handle. This means basically that those error terms don't follow the same distribution at all timestamps. And then the third challenge, which I believe is the most difficult to handle, that's going to be the non-stationarity that's present, potentially present in this type of data. Okay, so let me explain in those three examples from the beginning how those challenges appear here. So actually, it's quite obvious that in all three we have autocorrelation. The predictions at some timestamp are going to depend on the predictions of the previous timestamp. In all three, actually, you also have heteroskedasticity. So, for example, when the river level is high, then also our uncertainty about that river level, when we need to make a prediction, also our uncertainty will be bigger. The same for like gas prices or for COVID cases. Typically, the higher the prediction is or the ground truth is, the more uncertainty we will have. So you will typically have heteroskedasticity there. And actually, in all those three data sets, you also have definitely non-stationarity. We know that the climate is changing, but also for the gas prices, if Putin decides not to deliver gas anymore, then this is going to have an impact on the gas prices. So in all 3D applications, you also have non-stationarity. So let us think a little bit about those methods from the first part of the presentation, how these would behave in the time series forecasting setting. So for Bayesian methods, the kind of obvious problem is going to be that our errors often are not going to follow a Gaussian distribution. In the case of COVID cases, it's count data, which is not Gaussian, but also in the other two applications, we typically have observations that for which the errors are not going to be Gaussian distributed. For ensemble methods, here we already saw that for the classical regression problems, we don't get the kind of coverage in the intervals that we wanted to see. So those problems are also going to appear in the time series forecasting setting. So at least those simple ensemble methods would not be the way to go. Then for the direct interval estimation methods like quantile regression, I would argue that these are more promising, and actually the three challenges, the autocorrelation could be handled by using autoregressive features. The heteroskedasticity is something that's in fact immediately controlled for in quantile regression, and the non-stationarity could be handled by using some kind of online or incremental learning framework, like with recurrent neural networks or LSTMs. That's how you would handle the non-stationarity in these problems. And then for conformal prediction, we have the issue that the theoretical guarantees will not longer hold, because the theoretical guarantees only hold for an exchangeable sequence of error terms. And so maybe I have to explain a bit more in detail what an exchangeable sequence is. I'm not going to give the formal definition, but it means basically if you see like the sequence of the numbers 1, 2, and 3, then the probability of seeing those same numbers in a different order needs to have the same probability. Now, in a time series, that's not going to be the problem, because yeah, your sequence is fixed, and if those error terms are not IID, then typically you're not going to have the case that all sequences of error terms are equally likely to be observed. So we'll have to do some tricks to make those error terms IID in the time series setting, and if we can establish that, then conformal prediction could be applied. So for the remainder of the talk, I would like to focus a bit on how we could change conformal prediction in such a way that we can apply it in the time series forecasting setting. So the first challenge, the autocorrelation. So what's typically autocorrelation? You have autocorrelation in your error terms if you see like patterns over time. So on the horizontal axis, we have here the time. That you see a clear pattern in it, so that for example, if the previous one is positive, then the next one is also going to be positive. So here is an example of a positive autocorrelation. Here is an example of a negative autocorrelation. If at some stage the error is negative, then the next step is going to be positive, then it's going to be negative again. This is kind of something that appears, for example, in control settings. So we will have to do something to avoid that our error terms have this structure. And the way to do that is to build an autoregressive model that really has all the autoregressive features in there that you need to have to make sure that those errors become hopefully IID. And this means that we need to think about which variables to include up till which horizons. For example, here this is time step t minus s. If you have like seasonal patterns in your time series, you might need to go back quite far in time. So it's going to be a bit of an art to have this autoregressive model structure correct. But if you can establish that, then you can make that those errors are independent of each other. Now, this might be not easy to do. So for example, in some advanced applications, it might, for example, be the case that the prediction at timestamp t+1 also depends on the error at timestamp t. This is in situations where you can intervene in the environment. So if that's possible, then it's of course also required that you have these things incorporated in your model, or you will still see some kind of autocorrelation structure in your error terms. So that's about the autocorrelation. Then next question, how can we handle the heteroskedasticity? So let me also explain a bit what heteroskedasticity is. It can also appear in traditional regression problems. In traditional regression problems, where we have, for example, a predictive variable on our x-axis, it means that the variance is not homogeneous for different predictor values. So here you see that the variance increases when also the mean increases. So the variance is proportional to the mean. And this is also going to be like a serious issue in time series. So we'll have to do some things to get rid of this heteroskedasticity. Also for conformal prediction, this is going to be an issue, because if you want to apply conformal prediction in the presence of heteroskedasticity, it's going to imply that your conditional coverage, when you condition on a particular value for the response, that this coverage that you would like to have, that it cannot be achieved. So conformal prediction has this tendency, if it needs to have like a coverage of 95%, to really get this coverage from the easy cases. So typically on those 5% different cases, it will exclude those cases, and those are typically like the hard cases, the ones for which, for example, that are situated here, for which your variance is big, and we have seen in those 3 time series applications with the COVID cases and the water flooding that, yeah, in which situations do you want to have your prediction interval right? Just those difficult cases when you have a lot of patients in the ICU, or when your level of your river is really high. So without controlling for this heteroskedasticity, the conformal prediction is not going to be able to give the guarantees for those difficult cases. So there's actually in the literature 2 ways to resolve that. And the first way, I would say, is the traditional statistical way, by using variance stabilizing transformations. I will give an example on the next slide. The second solution is to use normalized conformal prediction. And what we're going to do there is we're not just going to look at the absolute residual here in the numerator of this fraction, but we're going to divide by the standard deviation for that particular instance. Of course, the standard deviation, we don't know it, so we'll have to estimate it, and that's going to be then the trick in this case, that we will have to estimate the standard deviation. So if you normalize those non-conformity scores, those residuals, then we can achieve this coverage in a more uniform way for easy cases and for difficult cases. So for the first approach, where we apply a variance stabilizing transformation, there's many transformations that have been proposed in the literature, but the kind of most popular approach is the Box-Cox transformation. It's a transformation with 2 parameters, lambda1 and lambda2, that's going to reshape your response variable, so that actually something that's not Gaussian distributed becomes Gaussian distributed. And those 2 parameters are typically fitted based on maximum likelihood estimation. So this is one approach. And then in the approach where we're going to estimate the variance, there's also different methods that do that. But kind of most popular approach is to have a neural network structure where you have 2 output neurons. So one output neuron is going to predict the mean, and then the second output neuron is going to predict our variance. And the 2 are connected in one neural network, and the 2 are connected by means of this loss function that you have here. So in this first part, we have the mean square error that we divide by the variance, and then you have a second term that tries to have this variance as small as possible. So that's an approach that you see in quite some recent machine learning papers. So then we end up with the third challenge, which is the most difficult to handle, I would argue, and that's the non-stationarity. Here I'm giving you an example of different time series errors that are non-stationary. So in the first case, it's a simple case of non-stationarity where you have a linear trend. This is a time series that can be made stationary by just subtracting this linear trend from it. In the second case, we have suddenly here at some timestamp that the errors are going to be on a different scale. So this is going to be a very difficult case to handle because you have a sudden shift, and the point I want to make here is that if this shift is too big and too sudden, you won't be able to give any guarantees anymore about your predictions. So the intervals you're going to return are going to be useless at that stage, and you'll need to have some kind of recover strategy or recover time frame to adjust your model to get your intervals right again. The same a bit with this situation here, where where suddenly the variance in our residuals is changing, and here this situation is a specific example of a unit root process that can be made stationary by applying a first order differencing transformation. So actually, in this case where non-stationarity is present, there's actually two ways to make your time series or to go forward. The first way is to apply a transformation that's going to make your time series stationary. If the non-stationarity is kind of simple, if you have some prior knowledge about what's causing the non-stationarity, then you could do that, like in this first example over here. And the second approach, if you have less knowledge about your non-stationarity, is to adjust conformal prediction so that it becomes robust against those shifts. And that's the kind of approach where we are experimenting with at this moment. Actually, we're experimenting with a specific method that was proposed recently. The paper is actually not published yet. It's on arXiv by a group from Berkeley. And how does this approach work? So you have a calibration data set of non-conformity scores that come from a distribution P. And then you have a test set of non-conformity scores that come from a different distribution P prime. And we're going to look at the F divergence between those two distributions. And we're going to assume that this F divergence is smaller than some value chi. Typically, in this paper, they also propose algorithms to estimate this high. So for the people that are not familiar with F divergences, it's a family of divergences to measure the difference between two distributions parameterized by a function F. KL divergence is a specific case of it. Under this assumption, they prove in the paper that you can modify your significance level of your standard conformal prediction procedure to have a guaranteed validity. So if you have a coverage level of alpha, you're gonna make a new coverage level in the following way. This alpha bar is going to be set in this way, where we have a function g and its inverse. I'm not going to go into detail, but this is how g and its inverse are defined. We see in this formulation that the f of this f divergence reappears in it. And then you can just apply conformal prediction as before, and you can guarantee that the ground truth is gonna lie in your prediction interval with a probability of at least 95%, for example, if that's the coverage level that you specified in the beginning. Now, we are applying this in the time series forecasting setting by estimating actually this divergence is a kind of measure for the shift you have in your time series over time. And we're using we're estimating actually this divergence in a moving window fashion. So also this high is something that's going to change over time. So then each time you apply a conformal prediction, and that's how we make it more robust. So for this last part, I didn't have experimental results yet because we're still working on the experimental results. So to conclude for the presentation, in the first part, I was talking about classical regression problems. And the point I wanted to make there is that many methods have been proposed in the literature, but there's very few statistical guarantees in the distribution-free setting. Conformal prediction has become popular recently, and in our experience, we have seen that it's a promising technique, and in general, it does what it promises. Now, for the time series forecasting setting, I've argued that this is a more challenging setting due to the presence of autocorrelation, heteroskedasticity, and nonstationarity. I'm arguing that when the change in the data is too quick, too sudden, then no guarantees can be given anymore in terms of prediction intervals. And at this moment, it's also still a bit unclear which methods would work here in the distribution-free setting. Of course, if you take some distributional assumptions, then there's a wide range of methods that can be used, but in the distribution-free setting, it's still a bit unclear which type of methods would work the best here.